So from the materials that we use to create our utensils to uh, home appliances, building materials for house, vehicles, um, rail tracks, and electrical towers for transmissions. We also use them in our power tools. Same time, even superheroes use them. Medical, it serves very important purpose in the medical field. At the same time, even false teeth. So maybe could be that we can use this, so they will play a very important role in our future spaceships, crafts, and of course missiles or mass weapons of mass destruction. So for today's video, we're going to have an overview of the applications and processing of metal alloys. So I'm Mark. So this is a topic in material science and engineering. So what I'm showing you is one of the topics that I presented back in my master's. So the reason why metals uh, are distinct from other materials is that because their electrons are delocalized. So it makes them, so with this property makes metals electrically and thermally conductive. So the premise is that when you combine two different materials, so you just make it stronger, and the combination of two or more metals is called an alloy. So if you can imagine, if you're going to include iron, carbon into an iron metal, carbon is not a metal, but it is a semicon. So if you're going to add impurities such as carbon to iron, you can make it stronger. So making it harder, unlike when you're using pure iron. But before we dig into the topics of the metal processing, which is alloys, let's go back first to the history. So it began when humans discovered that copper ore back in Mesopotamia in 6000 to 3000 BC. And then they realized that adding an impurity, probably due to I don't know, maybe accidents, that they were able to get bronze by adding tin into copper. Because if you're going to think of it, copper in its pure form is very malleable, so it cannot kill animals. So you all know that human back then, primary job is hunting. So malaking mammals, big animals, they have to kill it using tools. So they discovered it back around 3000 BC. So that's when they began crafting metals or bronze um, for many other purposes. That's why it's called Bronze Age. So yeah, Spartans back then. So that's the Bronze Age. So that's where we started using alloys. So alloys particularly are divided into two types. So when we say alloy, it is either ferrous metal alloys. So they are basically made from iron. Okay. So the reason why iron is chosen here is because it is abundant, it is easy to obtain at the same time, it is extremely versatile, which means that iron can be easily processed. So, but of course, there are also drawbacks in using iron. So one of which is it is heavy and it has low electrical conductivity, and it is very susceptible to rusting. So that's ferrous. On the other hand, we have non-ferrous metal alloys. So basically, non-ferrous metal alloys don't have iron at all. So they are basically anything that is shiny. Okay. So non-ferrous metal alloys are mostly made of almost anything except iron. Alright, so when you're using non-ferrous metal alloys, there's no corrosion. Now let's talk about the other types of ferrous metal alloys, one of which is steel. So steel is an alloy of carbon and iron. So the strength level of the steel depends on the percentage of carbon used. So steel metal alloys are divided into low alloy and high alloy steel. We also have cast iron, but let's talk about that later. Now, focusing on steel, there are two types. We have low alloy and high alloy. So for low alloy steel, we have again uh, the strength or the property of steel depends on the concentration of carbon. So when I talk about low alloy, we have low carbon steel, which has less than 0.25% weight of carbon. So they are soft, ductile, machinable, weldable at the same time. They're cheap, and they are mostly used in parts of ships and cars. And second, that we also have high strength alloy when we add copper, vanadium, nickel, and molybdenum to low carbon steel. So we can further improve low carbon steel by including copper, vanadium, nickel, and molybdenum to make it a high strength low alloy. Second one is medium carbon. So the concentration ranges from 0.25 to 6.6% rate of carbon. So they feature high strength and wear resistance, right? So based from their properties, they are widely used in parts of machines, which requires high strength and wear resistance, because wear resistance is where many of our machines are made of because they are turning. So mostly engine parts, yeah. And we can also further improve medium carbon steel by adding chromium, molybdenum, and nickel. So third type is high carbon. So the high carbon steel has a carbon content of around 0.6 to 1.4% weight. So they are can be further improved by adding chromium, vanadium, tungsten, and molybdenum to make high tension wires. So high carbon, low alloy steel are the hardest, strongest, and the least ductile. So that's why they are used in high tension cables such as suspension bridge, yeah, etc. So as again, if you just noticed, the more carbon content, the stronger it is. Yeah, stronger it is. So that's steel low alloy. We also have what we call high alloy steel. And high alloy steel are categorized into stainless steel. So stainless steel are types of high alloy steel which contains less than 1.2% weight of carbon and mostly added with some elements such as nickel and molybdenum. So when we say stainless steel, it is composed of chromium at 11% weight. So the features high resistance to corrosion and high thermal stability. So you might be wondering, there is a presence of iron here, but among all of the ferrous metal alloys, stainless steel has the strongest resistance to corrosion because of a higher concentration or percentage of chromium at 11% weight. Next is tool. So tools are the same stuff that we use in our drill bits and cutting tools, etc. So that's steel. Let's talk about cast iron, the second type of ferrous metal alloy. So cast iron, or also known as pig iron, contains at least 4% carbon. So they're made from coke. Um, they are actually made from coke in the process of hematite in a burning furnace. So here, the cast iron is a result of burning hematite in the cast burning. So as shown in the figure here, molten steel here, you have a slug here. So the reason why cast iron here is because it's basically um, cast iron is a very versatile one because they have a wide variety of uses. However, again, higher percentage of carbon makes it stronger, but it makes it more brittle. So that's the reason why iron or cast iron is a lot prettier, but it is much stronger than regular metal or ferrous metal iron. So the reason why is we're using them in our covers in manholes, the stuff that we use to cover our manholes, and some cookery. So cast iron are subdivided into many other types. So we have gray iron, ductile, white iron, malleable iron, and compacted graphite iron, and we're going to talk about them. So first, we have gray iron. So gray iron contains carbon and silicon varying between 2.5% and 4% weight perspective to 1 to 3% respectively. So they're mechanically brittle and weak in tension, but they are tough and ductile under compression. So they are used in the stuff that we use to, maybe equipments in the roads. So they're very strong in compression. So they also dampens vibration and they're also resistant to wear. Second one is we have white iron. So it gets its name from its color. So we use white iron, cast iron in rollers in rolling mill. We have pipes, wide tool ships, and heavy duty vessels. So we also used in our we also use this white iron in our conveyor belts. Next type is ductile iron. So it contains small amount of magnesium and cerium, and they were mainly used in valves from bodies and crankshafts. We also have malleable iron. Malleable iron is the one that we use from our pipe fittings. They also used in valves for railroads, marine, and other heavy-duty uses, and they can also only be produced in small quantities due to the high production cost. Right. So lastly, we have compacted graphite iron. So we use compacted graphite iron in our engines, so in the main hull of our engines. So here, carbon exists as graphite as the lubricant. So carbon content ranges from 3.1 to 4% weight. Also have silicon content from 1.7 to 3% weight, and some amounts of magnesium and cerium. So compacted graphite iron features high thermal conductivity, better resistance to thermal shock. Because again, if you're going to think of it, we use water to cool down the engine, and whenever we do that, we're going to explain later why heating metal is a bad idea. Okay, why it is a bad and sometimes a good idea to heat or to quench or to put water in hot metals. So also, compacted graphite iron features lower oxidation level at higher temperatures, which means that they are not reactive to our combustion. So maganda ito gamitin. So they use in diesel engine blocks, solid manifold, vehicle housing, brake disc, flywheels, etc. So nomenclature for steel is this is how we classify steel. There are because of a variety of steel that we can produce and the variety of steel that we can use for different kinds of purposes. It is convenient if we have something to name them. So we use here SAE, steel designation system. So this is the nomenclature for steel. So start with SAE, and then the first number indicates where this is whether this is carbon steel or alloy steel. So carbon steel, if 1 and 2 is indicates alloy steel. Okay. So second digit is modification in alloy. So when we say 0, this is plain carbon. And the last two digit is the percentage of carbon content in decimal. So that's it. So that's how we name different kinds of steel. So let's now we're finished with ferrous metal irons, and now we're going to talk about non-ferrous metal alloys. And these are anything that is shiny. All right. So let's going to have an overview about them. So first we have ferrous metal alloys, which is anything that is composed of predominantly of copper. So we have brass. So when we add zinc to copper, we have brass. When we add tin and phosphorus to copper, we have phosphor bronze, as you can see here. When we add tin, aluminum, silicon, and nickel to copper, we have bronze also as well, but a more shiny and sturdier one. When we have impurity, which is beryllium to copper, we have parts like this. I'm not quite sure what these are. When we add zinc and lead to copper, we have yellow brass. And when we have nickel added to copper, we have nickel. And when we have zinc at 30% weight, we have basyo ng bala ng baril. So that's copper. So one another interesting fact about copper is that it possesses antimicrobial property. So it is observed that bacteria, when they are on the surface of a copper, they die. Okay, so if you want to dig deeper about copper, antimicrobial property of copper, you can check research papers are published in Science Direct. So also one of the problem with copper is the copper corrosion. Even though that, again, as I said before, ferrous metal ions are very susceptible to corrosion, but I did not mention that copper is also susceptible to corrosion. And this is the reason why the Statue of Liberty now is greenish, because copper reacts to salt. Okay? But that's just it. It's just changing in color. So it's chemical reaction. So that's the alloys of copper. Now we have aluminum. So we have alloys of aluminum when we add copper, magnesium, silicon, magnesium, and zinc. So we have engine parts for airplanes. I'm not quite sure about this one. We also have parts for airplane here, and our iPhone, aluminum 6000 series. Okay, so we use aluminum. Alloys are very important because they are lightweight. Okay, so that's why they are very ideal to be used in materials for airplanes, because they are very light. Also to smartphones, because we don't want our phones to be heavy. Okay, so sturdy and heavy, we have aluminum. Okay, so we also have magnesium alloys. So these are mixtures of magnesium with other metals such as aluminum, zinc, manganese, silicon, copper, and zirconium, and they have applications in aircrafts and missiles. So magnesium is the lightest structural metal, which is very strong. So this is very heavily used in aircrafts and. Okay, moving forward, we use magnesium alloys heavily in aircrafts and missiles. Hindi rin kasi maganda yung ano eh, hindi rin kasi Alright, so very interesting, no? Because if you use the wrong material for missiles, so if you have a payload inside the missiles, so kapag sobrang matibay naman yung metal na ginamit doon, so kapag sumabog yun, mahina yun. Magiging mahina yung pagsabog kasi nga yung enclosure, which is the missile itself, is strong. So again, the trick for making strong missiles but at the same time very good material as bombs is if you're going to use magnesium alloy. So that's the reason why they're heavily used. So we also have titanium. Okay, so titanium alloys. These are very strong metals, but they are also very light. So when you want something which is very strong and light, you can look to titanium alloy. And as much as I'm concerned, really, Iron Man, the armor of Iron Man before uses titanium gold alloy. So titanium alloys are engineered materials because it's very difficult. The processing for the procedure for processing titanium alloys is very different. Because if you're going to think of it, they are tough even at extreme temperatures. So how do you process something which is very strong? Which is very strong, you know. That's the reason why. We also have refractory metals. So these are the metals that are extremely high. That has extremely high melting temperature. So these are materials that we are very good that we use in processing other materials that needs melting. Okay. So we also have super alloys. So these are used in aircraft turbine components, nuclear reactors, and petrochemical processing equipment. Okay, I'm not quite sure about those. And we also have some noble metals. We have gold, osmium, mercury, palladium, platinum, ruthenium, iridium, rhodium, and silver. Okay, so the point is we can add other impurities to gold, palladium, iridium, and silver. We can make other alloys of silver or mercury, whatever. Okay, so those are the types and the history of metals that we have here. And now we're going to talk about the material science or aspect of the metals. So what are these microstructures that we think? So before I begin with the microstructures, I'm going to establish first that the property of the metal depends on the microstructure, at the same time the composition, the elemental composition. So as I said, the property of the metals that we have here depends on the composition or the structure of the atom, at the same time the microstructure. Okay, so when we say electrons configuration, it is mostly chemical. But when we talk about microstructures, these are physical aspects which can be also considered as mechanical properties. Okay, so when we say microstructures, it is how the metals itself in a large in a bigger scale, in a bigger than atomic scale, are organized. So this topic is a lot higher. So before we dig into microstructures, you have to understand first the phases of metal or metal phases. Okay. Um, so if you want to check on those topics, you have to check other videos in the YouTube first. So, but I'm going to talk about microstructures and metals here in the assuming that you already know the microstructures in metals or phases of metals. Okay. So we have one of the microstructures predominant in metals is what we have of ferrite. So ferrite exists in room temperature. So this is very evident in pure iron with at least a very small percentage of carbon. So we also have austenite. Okay, so in terms of atomic structure, it is phase cubic centered. So this is an example of austenite here. So when we say that the face of the metal is in austenite, so it arranges in a diagonal or linearly. So it is an iron carbon alloy phase that happens at temperatures above 723 Celsius and below. So it means that austenite happens at between temperatures of 723 degrees Celsius. So this is heated iron carbon alloy. So that is happening austenite. So we also have martensite. So martensite, or what they say monoclinic arrangement, is where atoms arranged in diagonal form. So appears when austenized iron carbons are rapidly cooled. So quenching. So later I'm going to explain quenching. So thus stopping carbon ions to diffuse, trapping them in clusters. So we also have cementite. So cementite is basically present in all iron carbon alloys having 6.7% weight carbon and above. So this is what you see. Okay, so this is what you see whenever that there is an iron carbon that contains 6.7% weight of carbon. So we also have number 5, perlite. So perlite appears when metal alloys are heated then slowly cooled. So contrary to martensite here, rapidly cooled. Okay, so perlite here allows the carbon to diffuse, because when we subject materials to martensite rapidly cooled, so natatrap yung mga carbon clusters. So here in perlite, you allow them to cool. Okay, so the main one of the distinct characteristics of perlite is that they are soft, they are also ductile to a bit hard, and they are also brittle. Okay, so perlite is a combination of ferrite structure and then cementite. So we have ferrite here before, okay, and we have cementite here. So ferrite plus cementite, we have perlite, that structure that looks like this. Now, so why am I discussing these things? Okay, so the reason why I'm discussing these things is because arranging, for example, a block of cement or concrete hollow blocks. So the way that we arrange concrete hollow blocks determines the strength of the wall. Okay, so there are different kinds of configuration of walls or wall arrangement of blocks for walls, and they have different they also have different disadvantages and advantages. And the way that we arrange them greatly determines the strength of the structure. And it's the same thing. It's the same thing here in metals. Okay, so question is, which of the two cement blocks arrangement is stronger? So if you're going to look at this one, this is a lot stronger than this one. Okay? So what's the point here? So the point is, even the tiniest changes in the microstructure changes the overall characteristics of the metal alloy. So just a very tiny change. So it affects the overall. It affects the overall details. So there's also a question in the book. So it says here that it is possible to produce cast irons that consist of martensite matrix in which graphite is embedded in either flake, nodule, or reset form. So briefly describe the treatment necessary to produce each of these microstructures. So how do you produce a cast iron with either flake, nodule, or reset form? So we're going to understand this one using our phase diagram. So phase diagram here shows how we're going to produce cast iron with flake, nodule, and reset form. Okay? So looking at this one, at this phase here, okay, so increasing the temperature here from ferrite plus graphite here, we can increase them to this phase here. So flake. So it is possible. So whenever that we have a concentration here of cast irons between 2 to 4%, whenever that we increase the heat here, okay, so increasing the heat can give us the property that we want. So we have a ferrite here. So it is possible. It is possible if you're going to heat it. So ferrite will transform to austenite. Okay. So transform rapidly quench to austenite, produce martensite where carbon can arrange in flake nodule. Yes. So the answer is yes, it is possible by heating the cast iron here at ferrite. So ferrite area, ferrite here, ferrite, and then we heat it and then we quench it to produce martensite. Yes. So from the iron carbon phase diagram, composition ranges for commercial cast iron. So we have 4% carbon weight here. Okay, so schematics microstructure that result from a variety of heat treatments here. So question is, briefly describe the heat treatment necessary to produce flakes, nodule, and reset form. Okay, so here, okay, so higher concentration here, cementite at 6.7% carbon. Alright. So this is the range. So the same thing I showed you before here. Yeah, here. This area. So perlite, ferric. Okay, so graphite of GF, GR, GN, ferrite, and A, ferrite. Okay. So fast cool, we have white iron. When we moderate cooling, we also have ferritic. Slow cool, we have ferritic gray cast iron. Okay. So we we can heat the cast iron here and then subjecting it to fast cooling, which is by quenching to produce martensite. And then we reheat it again at 700 degrees Celsius. Then that's for 30 plus certain amount of hour. We can either fast cool it again and then or slow cool it again to get ferritic or ferritic. Yeah. So that's the overall here. So this is important here. So you can only have this kind of property if you have a certain if you use cast iron, if you use if you use a ferrous metal alloy that has a concentration of carbon around here. So these are the treatments. So if you heat them at this position, at this concentration, this at different temperature. So again, going back here, if you heat them at 600 degrees Celsius, you will only have ferrite. But once you increase temperature here at around 8,000 to 1,000, around 1,100 degrees Celsius, you will have you will have yeah. Okay, so that's what you're going to have, perlite. Okay, then white iron reheat. So you fast cool and then you heat it again to 700 degrees Celsius to sustain to sustain the ferrite to martensite, and then fast cool or slow cool. Very interesting. So now that's a topic that we introduced, that when we heat, or the way that we treat the metals during their different phases affects the arrangement of the atoms and also the microstructure. So it also gives us a different property of the material. So that's when we talk about the microstructure. But what if we are not quite sensitive about the microstructure, but we just only going to focus on the fabrication methods and techniques. So there are many kinds of fabrication techniques in metals. So of course they are categorized into three. We have forming, we have casting, and we have other types of fabrication techniques. So first one, we have to understand first the terms, or the method employed here. So as again I mentioned before in the earlier slides, heating the metal to a certain temperature and then elevate and sustaining the temperature of the metal at that. And the property of the metal is changing whether you subject it to slow cooling, rapid cooling, or cooling at a normal temperature. So how you introduce the cooling affects the property of the metal itself. So here in the fabrication aspect, we only have two. So we have cold working. Now, what is cold working? So cold working, from the name itself, is not really cold, but cold working is is fabricating a metal without using heat. So this is only a room temperature. So the benefit of using cold working here is that you can increase the strength and improve the mechanical properties, such as later. So it's also processing at room temperature. So if you subject metals to cold working, you will get a high quality surface finish. So this is very smooth. So cold working is what we do when we want to polish or shine a certain metal. So that's a good thing. But the bad thing about cold working is that it decreases the metal's ductility because it becomes very stiff and strong. And more force is needed for plastic deformation. So more force is needed for you to scratch, to shine, or to polish the metal, because the metal in cold state is strong. On the other hand, when we talk about hot working, so of course, medyo malambot, mainit. Okay, so since it is buttery soft, you can introduce large process deformations. You can really change it to whatever form that you want. So deformation energy needed is less because it is very soft. But the downside of using this is material loss to surface oxidation, which I'm going to show later. And we also have poor quality surface finish because that's the downside of using hot working. So, magaspang. At may mga pores sa mga lubak-lubak. Okay, so first type is forming. So, those are the two types. So, you can either cold work it or hot cold it. So, those are only two. But the fabrication method itself is divided into three. So you can either do forming. So what is forming? So first example of forming is by hammering or stamping. So when we use wrenches, crankshafts, so here you have a blank or a solid block of metal. And then you're going to compress it, and then you're going to have this kind of shape. Okay, so that's forging. Heat it up like this, so heating and then hammering. So yeah, so this is what I said, material loss here. So you get material loss whenever you are hot working a metal. Second type of forming is rolling. Okay, so this happens when you roll the certain metal or metal sheet. So also rolling is also used in if you want to make very thin sheets or wires, you can also do rolling. Okay, so sorry pa, very thin sheets lang pala. But when we want to produce wire, we use drawing techniques. Okay, so this is an example of drawing techniques here. Okay, so this white is the wire itself. So this is the bigger diameter. This is smaller diameter. This is the drawing process. So we use this when we want to make rods, wire, and tubes. So fourth type is by extrusion. Okay, so when we compress a metal, it heats up, then that heat is enough for it to melt. Okay, so that's extrusion of a billet. So we're done with forming, and now we're talking about casting. So casting, first type is by using sand. So sand casting is used when we want to produce large parts. Okay, so this is the process of casting. So second one is investment casting. So you use the type used is investment casting when we are producing low volume. So example, jewelry. So there are actually three phases or stages. So one is you're going to create the mold first. The second one is you're going to apply the wax. Okay, so there is there is a hollow space, and then you're going to pour the metal that you want to form. So that's the investment casting. So this is an example of investment casting or using ring to produce a ring. The third one is die casting. So yeah, just like that. So you put the pellets, then you heat it, and you form it. Okay, just like this. So split the die, then you're going to put inside, inject a liquid metal, and then you release it to make it. Once it's already cold. So we also have continuous casting. So for simple shapes, as in tabular slabs and cylinders. So just like that, that's continuous casting. So what are the other types? So first one is powder. So you powderize the metals. I think this is very useful if you want to reprocess scraps, or for example yung mga kiskis, pag naipon mo, so pwede mong gawin yan. So that's powder metallurgy. So you compress the fine powders, and then that heat build up is enough for it to melt. So it's the same thing. So you also have welding. So welding is another metal fabrication method. So when fabrication of one large part. So we use welding if we want to join mm, many other parts. Okay, that's what we do, welding. So the very interesting here is that when we use welding, there are difference in the faces in the structure, and also at the same time the physical appearance of the heated area, because this is where microstructure has been changed. So it's different from the metals or the parts joined. Alright, so that's the metal fabrication methods. We have forming, casting, and we also welding, and then powder metallurgy. Right, so now we're going to talk about the thermal processing. So before, we talk about the mechanical part, mechanical aspect, and now we're going to talk about the thermal processing. So this is how heat affects the property of the metal itself. So there are many kinds of annealing. So first we have stress relief, and we use stress relief annealing to reduce stresses from classic deformation, from cold working, and non-uniform cooling and phase transform. So we also have periodize. So we make this is for us to have very soft steels for good machining. So cold working, good machining. Heat just below eutectoid temperature, cold for 15 to 25 degrees at 15 to 25 hours. We also have full anneal. So here we make soft steels for good forming. So heat to get then surface cool to obtain coarse perlite. We also have normalize. So we normalize to deform. So when we have deformed steel with large grains, so we use annealing to normalize the large deformations. Okay, so we pull them and then heat them again. Then the heat treat to allow recrystallization and formation of smaller grains. Smaller grains means higher strength. Last one is process and anneal. So using process anneal to negate the effects of cold working. So after cold working, you can use process annealing to negate the effects. So here you're going to recover recrystallization to make smaller regions, smaller grains. So annealing in a nutshell is like relaxing or conditioning a metal alloy from extreme stress due to temperature and deformation. So in temperature, when we if we hot work it, and deformation whenever that we do cold deformation or plastic deformation. So annealing, so basically annealing allows the atoms to arrange to recrystallize, so making it workable again. Okay, so these are annealed metals. So as you can see again, as I said, we can anneal metals to make them workable again. But hardened metals are very strong, stiff. Alright, so hardenability steels. So hardenability. So this is how we measure this is how we test metals in terms of their hardness. Okay. So we use Jomini and Quench. Though I'm not quite sure about the process, but theoretically this is how the process works. So this is the metal or subject specimen, and then we inject a water or splash the metal the specimen at 24 degrees water. Okay, so there will be hard a rock will see hardness test. I'm not quite sure about this one though. Oh, so we test the hardness here. So this is for example, we heat this specimen to gamma phase, and then we quench it with 24 degrees water, and then we try to scratch the surface. Okay, scratch the surface, and then we plot the hardness. So it says here that we get higher hardness as we increase the distance from the end point, which is quenched. So So the shorter the distance, the higher the hardness. Then it means we have a very hard metal or steel. So that's the basic concept. That's the science behind it. So this is the plot. This is the plot hardness for different kinds of metal alloys. So we have 1040. So it means that this is carbon non-modified 0.4%. Yeah, 0.4%. This is a different. This is a ferrous. Non-ferrous rather. These are non-ferrous. As you can see here, what this means is that um, carbon steel that has 0.4% carbon is stronger than all other metals. That's the meaning. Because at a very short, only at a very short distance from the quench end, you have a high hardness. But of course, they possesses higher hardness than the carbon. Obviously, because these are already combination of other metals. So these are higher concentrations. So quenching have different effects as well to the metals. So it depends actually on the medium. So quenching medium can either be air or oil or water. So it also has a severity of quench. So when we have air, we only have a very low quenching because air is not a very good. So the of hard effect to the hardness when we use air is quite slow. So what's a good quenching medium is water. Because when we use water, you have a high quenching rate and the hardness we get a very high. So what this means that we heat the metal and then we quench it to make it strong. So I'm going to give you an example later. The purpose of quenching. Okay, so this is quenching of a sword. So quenching is used to process in making swords to make it very strong. But mind you that strong is also brittle. So it's strong but brittle. So I think that's the downside of making something which is strong. You make it brittle, right? But it is strong, but it's brittle. So that's a process. You use quenching to make it very strong or hard. Oh, now so remember the it's very important for us to consider the geometric size of the specimen because if you're going to quench the outside of the metal here rapidly, you will still have a very soft or hot core inside. So it's very important. So if very important for you to consider this because if the outer is hard and the inside is soft, then it is very prone to breaking. So in order for you to make a very good sword, you must have a mastery. So you must have a very high experience because quenching the metal itself is an experience. So you have to you have to subject the metal to quenching. Consider it that the the outside as well as the inside is quenched, so it's okay. You don't want a sword which is hard on the outside but soft in the inside. You don't want that. So this is also the secrets to do a famous sword. So making good swords is depends on the quenching technique. Okay, so as you can see here, as I said before, so this is the outside of the sword, and what you see here on the middle part, okay, if the sword was not quenched properly, then the inside will not look like this. So it will have a different it will have a different face. So that's the reason why. So this end is purely martensite here because you can see the fibers is densely compact. So this is purely martensite and this is the strongest part of the sword. But it is also the most brittle. So So martensite formation also happens here, but a very low, okay, the middle. So it means that this katana has been quenched properly. So I'm not going to talk about this one. So, so summary overall, there are two kinds of ferrous alloys. We have steel and cast irons, and the the strength or the property of the steel depends on the concentration of carbon. Okay. However, on the cast iron, it's just very complicated. So considering the fact that cast irons have more than 4% carbon, they're strong. But what's but what makes them different from steel is you can tweak them. What I'm saying is, um, they have a wide variety of uses. At the same time, um, they have their applications or their methods of processing or fabrication is a lot more complex. Sometimes complex than steels. So that's the reason why. So this is the difference really. We also have non-ferrous alloys. So anything that is not composed of ferrous or iron are non-ferrous. So also have metal fabrication techniques. So we have forming, so many types of forming. We also have casting, so several types of casting. And for under miscellaneous, we have powder metallurgy and welding. So the hardenability of metals can be measured using Johnny metal test. Okay, so it is very obvious that increasing the alloy content results to a higher hardened material or metal. So we also have precipitation hardening a while ago. Okay, so yeah, so that's the overview, or that's the overall summary of the metal processing. So I did my best to give you an idea about them, but to give you more in-depth knowledge about them, you have to consult materials engineer for this one because they have a wide range or depth or information about metal processing, the phases of the metal, and how treatments affects the properties. But in my so I hope you learned a lot for today. May this be give you a may this give you an idea how we process metals. Okay, so thank you. Bye bye.